moving away from it a little bit. We're going to be doing some more things other than just verifying and simplifying. But we're not going to move away completely from it because the reason that we verify and simplify is still going to be coming up. Because, like, the verifying and the simplifying, it's not necessarily about just that. Okay, maybe the verifying actually is. You're testing to see if two things are the same. Because it's not uncommon in the real world situations in which trig comes up that people will end up getting different equations, and you want to check that you are really getting the same thing. That's the point of the verify. It's two people got these answers. Is it the same? The simplify is going to come up when we get into 13.5 at the end of the chapter. So we're still going to be doing a little bit of verify, but we've got some new identities. So you're going to need your identity sheet and your unit circle today. Today we are bringing in the sum and the difference identities. So we've got 6 sum and difference identities. They're on the top of the back side of our identity sheet. I am not going to break down where these identities come from so much. They're more of a pain in the butt to show. We're just going to dive in and start using them. Now, one of the ways that we can use these identities is these identities are actually another source of cofunction identities. So one of the things you can be asked to do is to verify a known identity. The cofunction identity that we are going to verify is cosine of pi over 2 minus theta being equal to sine of theta. Now, if you're trying to verify this identity, can you use this identity to verify it? No, you cannot use the cofunction identities to verify a cofunction identity. It's not how it works. So this is where our sum and our difference identities can come into play. When it comes to using the sum and the difference identities for verifying, the big thing you've got to look at, because generally speaking, these ones don't show up a whole lot in the more complex verify ones. These ones just kind of show up in something that looks just like this. When it comes to using these, you really just kind of have to figure out which of the identities does it fit and start plugging things in. Okay, so you just have to figure out which identity is it that you're going to use. So I see cosine of two things getting subtracted. That's where you're going to focus in on. So we're going to use the cosine and subtraction. Is that a sum or a difference? A difference identity. Now the big thing that people screw up when it comes to this identity is notice that the identity says cosine of A minus B. In other words, the minus is built in. That B, that second term, is not negative. It's just being subtracted. So when I plug it in here, it's a positive number. So I'm going to change this using this formula. A is the pi over 2. B is the theta. Because it goes A minus B, and it's pi over 2 minus theta. So this side becomes cosine of pi over 2 times cosine of theta plus sine of A is pi over 2 times sine of B is theta. Do you notice you have trig of a known angle? Don't we know trig of pi over 2? Isn't it like maybe on the unit circle? Find pi over 2. What's cosine of it? 0. 0 times cosine of theta plus sine of pi over 2. What's sine of that angle? 1 times sine of theta equals sine of theta. What's 0 times cosine? 0. What's 0 plus anything? Whatever we added it to. What's 1 times sine? So what's this simplify to? Sine of theta equals sine of theta. Done. That's how these sum and difference identity verify problems will look like. That's as complicated as they get. Sometimes they might have different angles here. Okay. Can you do trig of different angles? Yeah, particularly they're going to be on the unit circle if they do different angles. So you just use the unit circle after you've split it up. Okay, now, to be honest with you, that's not going to be the main thing you see, though. More than often, in this section, you're going to see problems that are going to ask you to find the exact value of something. And we've come across problems that have said this in the past. We've been coming across problems that say find the exact value of, and then it will say something, since 12.3, which was like week 2 of the trimester. So we've been doing this for a while. But as we continue to move on, sometimes the problems will change a little bit. Back in like week 2 of the trimester, we would come across problems like this, sine of 3 pi over 4. 3 pi over 4 is on the unit circle, so we'd look at our unit circle, we'd find where sine is, and sine is what part of the unit circle? The y values. So we'd find the y value at that coordinate point, and we would find it to be square root of 2 over 2. And then we would move on, because we did exactly what we needed to do with this. Is every angle in existence on the unit circle? No. So, this leaves a lot to be desired. We are able to find, I think it's 16 angles and all of its coterminal angles using the unit circle. But what about the rest of the angles? What if I wanted to do something more like sine of 105 degrees? This is where the sum and the difference identities can come into play. Now, they don't always work out nicely because there's a lot of angles that won't work with the sum and the difference identities. Because if I want to use a sum or a difference identity to evaluate this, first off, I recognize its sign. So it's going to be one of my sign identities that I'm working with, either a sum or a difference. If I want to be able to find an exact value, then when I plug these into here, and I get my sine of A, cosine of A, sine of B, cosine of B, I want to be able to evaluate those. The only way I can nicely evaluate an angle and get an exact value is if it is a unit circle angle, which means this sine of 105 degrees, I want to break it up into either two things being added or two things being subtracted that are angles on the unit circle. So we're working in degrees. So I'm going to look at the degree angles on the unit circle, and I'm going to ask myself, is there some way I can grab two of those angles and have them either add or subtract to get 105? 60 plus 45 is one option. 135 minus 30. We could go on for a while. There are a lot of different ways that we can do this. We just have to pick one. Whichever option we pick, in the grand scheme of things, we should get the same final answer. Let's say we chose to do 60 and 45 being added, because that's honestly where my brain goes. So, sine of 105 is equal to sine of 60 plus 45. Not sine of 60 plus sine of 45. No, it's not how addition of trig works. The 60 and the 45 are both still in the same trig. The first angle's A, the second angle's B, because the identities go A plus or minus B. Since we chose something that added, we're going to use the sum identity, which says sine of A plus B is sine of A times cosine of B plus cosine of A times sine of B. So that means sine of A was 60 times cosine of B was 45 plus cosine of A, 60, times sine of B, sine of 45. From here, we can evaluate each of those individual trigs. What is sine of 60 degrees? Square root of 3 over 2. Times cosine of 45 degrees. Square root of 2 over 2. Plus cosine of 60 degrees. 1/2. Times sine of 45 degrees. Root 2 over 2. From here, it's just a matter of simplifying what we can. Simplifying is following PEMDAS. Do I want to subtract or multiply first? Multiply. To multiply fractions. Straight across. Square root of 3 times square root of 2. They're both inside square roots, so they do multiply. Square root of 6. 2 times 2. Over 4. Plus 1 times square root of 2. Square root of 2. 2 times 2. 4. Now I add. In order to add fractions, I need a common denominator. That's nice of them. Square root of 6 plus square root of 2. Can I add square roots? No. They're not like terms. It's square root of 6 plus square root of 2 all over the common denominator of 4. And that's as simple as it gets. That's our answer. Nothing too scary so far? Let's try another. This time I want to do a subtraction. You don't always have to choose subtraction or addition. I just am choosing on this one. I want to do one with subtraction. So I need two angles that subtract to get 195. 225 minus 30. Are there other options? There's always other options. 240 minus 45. Oftentimes I have people tell me 200 minus 5. 200's not on the unit circle, neither is 5. Make sure they're on the unit circle. I was told 225 minus 31st. Try it out. See if you can go from there. was minus a negative, you want to change it to a plus. Adding a negative just becomes a minus. Does the cosine subtraction identity go cosine sine or cosine cosine? Cosine cosine, you got to be careful of that. Cosine and sine identities switch back and forth. The cosine ones go cosine cosine. The sine ones go cosine sine. The other thing you have to pay attention to, that you have to be careful of, is it addition or subtraction? Because those switch depending on if you've got plus or minus or if you're doing sine or cosine. Does the cosine have a plus or a minus there for a subtraction identity? It's got a plus sign. Negative square root of 2 over 2 times cosine of 30 degrees, square root of 3 over 2 plus sine of 225, negative square root of 2 over 2 times cosine of 30 degrees. Did I write cosine? That's not supposed to be cosine, is it? I was saying sine and cosine too much as I was writing it. Let's try that again. Sine of 30 degrees. 1/2. Multiply those. What do I get? Negative square root of 6 over 4. Multiply those. I get? Negative root 2 over 4. I add them. Does it become a negative root 4? No. Becomes negative root 6 minus root 2 all over 4. That is one acceptable way to write the answer, but you have to be careful of where you put your negative. Oftentimes when we have negatives at the beginning of fractions, we like to pull them out front, and that is accurate that you should do that. But if I were to move the negative right here and then have my fraction, square root of 6 minus square root of 2, that negative now is being placed on both of those. If I put a negative on a negative, is it still negative? No. I will tell you right now, oftentimes they will put the negative out front, but to do so, they're factoring it out. They're saying, I'm going to divide both of these by a negative, put the negative there, and therefore this is addition. I'm okay if you leave it like this. If you are a person who uses the back of the book to check your answers, because if you didn't know this, our book has odds in the back of the book. It has the odd answers. This is how the book will answer it, is it will factor out that negative. It won't leave a negative in very front of a fraction. Okay, so working with these sum and difference identities, nothing too scary about it until you get to tangent. Now, what makes tangent a little scarier is the identity itself. The tangent identities are all fractions. Our trig of things on the unit circles are typically fractions. So when you're working with this, we've got a couple of problems. First off, we're going to have fractions in fractions. In other words, we're going to have complex fractions. You can't leave complex fractions in a simplified answer. So you've got to simplify that complex fraction, unless you avoid the complex fraction altogether, which is possible. And the second problem is that it's putting trig in a denominator, which is great and fine and dandy, because we're going to switch it out with a number, so it's fine, except for the number we're switching out with most likely has a square root. Can we leave square roots in denominators? No. So tangent tends to become a little bit trickier, especially if you're not careful on which angles you choose to get your angle. Tangent of 15 degrees, you can get it a lot of different ways. Most commonly, people automatically say 45 minus 30. Real simple way to get subtraction, and I will tell you right now, It's one of the worst ways to go. Here's why. Look at your tangent on your unit circle. Is tangent always or even typically a fraction? No, most of the time tangent isn't. And if the identity has fractions in which we can plug things into, if we can avoid plugging a fraction into said fraction, we're going to save ourselves some work. Will it work? Absolutely. Do we want to deal with it if we don't have to? Absolutely not. So, avoid the fractions. In other words, with tangent, avoid anything that has a 30-degree reference angle. Remember the reference angle, the acute angle that it makes with the x-axis? This is a 30-degree angle. Technically, if I was measuring from here to here, that's a 30-degree angle. From here to here, that's a 30-degree angle. From here to here, that's a 30-degree angle. That sound familiar to reference angles from back in chapter 12? So avoid those 30-degree reference angles. In other words, avoid the square root of 3 over 3's. Find another way when it comes to tangent. Can you do it this way? Again, absolutely. You gonna save yourself some work by avoiding them? Yes. So when I try to do tangent of 15 degrees, I'm gonna find two things that, well, they're not gonna add to 15. So two things that subtract to 15 without using the 30. 60 minus 45. So, it's subtraction, it's tangent. That's my identity I'm using. 60 is the A, 45 is the B. Is it 45 or negative 45? 45. The negative, the minus is already included. Okay, so this becomes tangent of A, 60, minus tangent of B, tangent of 45, over 1 plus tangent of 60 times tangent of 45. Tangent of 60 degrees, square root of 3, minus tangent of 45 degrees, 1, over 1, plus tangent of 60, we just said was root 3, and tangent of 45 was 1. If I go to simplify, do I really need square root of 3 times 1? No. Square root of 3 minus 1 over 1 plus square root of 3. I cannot leave that because I cannot leave square roots in the denominator, so we are not done with this one. How do I get a square root out of the denominator? Multiply on top and bottom, but when there's a plus or a minus, is multiplying by the square root of 3 going to do it? No, you multiply by its not reciprocal. Starts with a C. I heard someone whisper it. Conjugate. Conjugate of the denominator is 1 minus the square root of 3. Remembering that when you're multiplying by something with a plus or a minus, it is technically in parentheses. There's parentheses here, and here, and here, and here. And just a little note to self, that's the conjugate of the denominator. I'm going to have to do some FOIL. Both top and bottom. Square root of 3 times 1. At least it's easy multiplication. Square root of 3. Square root of 3 times a negative square root of 3. negative square root of 9. If you knew that was negative 3 right off, go for it. Negative 1 times 1. Negative 1. Negative 1 times negative square root of 3. Positive square root of 3. All over. 1 times 1. 1 times negative square root of 3. Negative square root of 3. Square root of 3 times 1. Positive square root of 3. Square root of 3 times negative square root of 3. Negative square root of 9. By the way, could I cross things off right now like the negative square root of 9s? No. Remember, you can only cross things off on the top and the bottom of the fraction if they're in a fully factored form. In other words, no pluses or minuses, not in parentheses. And by putting them in the parentheses, they're not matching perfectly. Can I cross some things off? Yeah, I got a negative square root of 3 and a positive square root of 3. Death to them both, because they're getting added. Okay, so I see these square roots of 9s. I know those are 3s. I combine my like terms. Negative 3 minus 1 is negative 4. What's the square root of 3 plus the square root of 3? 2 square roots of 3. You cannot add square roots if they're not like terms, but if they are like terms, in other words, the radicand, the number inside, is the same, you add them like you do x's. An x plus an x is 2 x's. A square root of 3 plus a square root of 3 is 2 square roots of 3. Over. 1 minus 3 is negative 2. We simplify the fraction if possible. We can simplify the fraction if all of the integers, there's going to be 3 of them, if all 3 of them divide by the same number. Negative 4, 2, and negative 2 all divide by 2, or more accurately, because I don't want the negative on bottom, negative 2. Has to be all 3 of them. It's always going to be 3 of them. Since they do all divide by a negative 2, I get 2 minus 1 square root of 3. All over 1. Do I really need the over 1? Do I need the 1 in front of the square root of 3? Also no. More commonly, it's just 2 minus square root of 3. If you leave the 1 there, I'm not upset about it. So, tangent can become a little more beastly, but it's workable. Okay. I got a couple more examples that show a couple of other things that pop up that mess with people, but otherwise it's the same process. This next one actually holds 2 things that mess with people a little bit. Secant of 11 pi over 12. Is there a secant identity? No. How do I typically do secant of something? Find the cosine version of it and then do its reciprocal. So, yep. Okay, that addresses one of the things that trips people up, is how do we deal with those reciprocal identities? The second thing we have to deal with is, are you easily finding 2 things that add or subtract to 11 pi over 12? For some of you, absolutely, because you're really good with fractions. For many of you, is kind of the reaction. Is my final answer an angle? Is 2 minus square root of 3 an angle measurement? No. And if my final answer is not an angle, does it matter if I keep my current angle in radians? No. We keep units if the final answer still has that unit involved in it. We keep radians if our final answer is something in radians. This isn't something in radians, so convert. How do I convert 11 pi over 12 into degrees? Multiply by 180 over pi. Pi's cancel out. 11 times 180 is 1980. Divided by 12 is 165. So, secant of 11 pi over 12 is equivalent to secant of 165 degrees. I'm going to find cosine of 11 pi over 12, in other words, cosine of 165 degrees. I need two things that either add or subtract to give me 165. 135 and 30? Sure. Okay. Cosine, cosine, or cosine, sine? Cosine, cosine. Cosine of 135 times cosine of 30. Second part goes sine of 135, sine of 30. Plus or minus? The cosine identities, the addition identity has a minus sign, the subtraction identity has a plus sign. Cosine messes everything up, sure. Okay. Cosine of 135 degrees. Negative square root of 2 over 2. Cosine of 30 degrees. Positive square root of 3 over 2. Plus sine of 135 degrees. Square root of 2 over 2.
Isn't it supposed to be subtraction?
Is it supposed to be subtraction? Is cosine the one? No. Oh, yeah. I mentioned that it was supposed to be minus, and then I wrote a plus sign, didn't I? We even talked about cosine messes everything up. Is it really cosine that messes it up, or is it Benson? I promise I didn't make the identity. So, I'm going to go with its cosine. I don't know what you're talking about. It was a minus there the entire time, obviously. Okay, anyway, back to sine of 30 degrees. 1/2. When I'm simplifying these, do I subtract or multiply first? Multiply. I get a negative square root of 6 over 4 minus the square root of 2 over 4. Doesn't that look kind of familiar? You'll find that the sum and the difference identities very, very, very often for sine and cosine will have square roots of 6, square roots of 2s, and over 4s. The difference will be what's positive and what's negative. Negative square root of 6 minus square root of 2 all over 4. Is that what I was looking for? No. Remember to switch it to secant. So secant of my original 11 pi over 12 is the reciprocal of this. 4 over negative square root of 6 minus square root of 2. Can't leave negatives or square roots in the denominator. What's the conjugate of the denominator? Negative square root of 6 plus square root of 2. You do not change the sign on the first term. Far too often people try to change the sign on the first term. It's not going to do you any good. Remember, you're going to have to do some distribution. Anything with a plus or a minus is technically in parentheses. I'm distributing the 4 to this. 4 times negative square root of 6 is negative 4 root 6. 4 times square root of 2 is 4 root 2. Over. Negative square root of 6 times a negative square root of 6, positive square root of 36. If I recognize it's a positive square root of 36, can I jump directly to positive 6? Yes. If you don't do that, that's okay. You're going to get there eventually. In fact, you can also recognize that by these being conjugates, when I FOIL it out, I get 4 terms, and the middle 2 are always going to cancel. So you could also skip multiplying the middle 2 if you want. If you don't, it's not the end of the world. I get a negative square root of 12. I get a positive square root of 12. And then the last one, negative square root of 2 times positive square root of 2, negative square root of 4, in other words, negative 2. I didn't do the canceling right away, so I'm going to do that now. And I get 6 minus 2, which is 4. Can I simplify? If all of those integers, there's an integer in front of every square root, whether you see it or not, they all divide by 4, giving me negative 4 square root of 6. No, not negative. Oh my goodness, Benson, get it together. Apparently today it is. Benson screws it all up. Let's try this again. Dividing by 4. Negative 4 divided by negative 4 is not negative 4. It's negative 1. I can do this. I promise. Negative 1 square root of 6 plus 4 divided by 4 is 1 square root of 2. Do I need the ones? No, they're like coefficients. Negative square root of 6 plus square root of 2 is the more common version of what you'll see. You might see an answer key tell you it's square root of 2 minus square root of 6. Is that equivalent? Yep. Okay. There's one last thing I wanted to show you. I unfortunately ran out of space. I don't need a whole lot of room. So if you're towards the end of a page and you've got a couple of lines left, you're fine. I have no lines left. The last thing that'll mess with people. Really big angles. We've dealt with the really big angle thing before. Didn't we always just do coterminals? You can do coterminals with this too. Add or subtract a full circle in degrees. 360. It's too big, so I'm going to subtract. I subtract 360. And what do I get? $915. I heard it finally. Is that easy to work with? No, I do it again. $555. Still probably not the easiest thing to work with. I could. I would be working with some angles in the 200s and I would get there. Is it obvious? No. I'm going to do it again. 555 minus 360 is 195. Is that doable? Yeah, that is doable. In fact,
We did that exactly a couple.
we already did it. Cosine of 1,275 degrees is negative square root of 6 minus square root of 2 all over 4.